Have you ever wondered how benzene and aromaticity work in chemistry? It's a question that piques the curiosity of many. So let's start with benzene, an organic chemical compound with a molecular formula of C6H6. This compound is made up of 6 carbon atoms joined in a ring, with 1 hydrogen atom attached to each carbon atom. Benzene is not just any ordinary compound, it's a cornerstone of organic chemistry, playing a pivotal role in the synthesis of a vast number of chemical compounds. Now let's touch on aromaticity, a distinctive property of certain cyclic planar molecules. Aromatic compounds like benzene exhibit unusual stability compared to other compounds, thanks to their conjugated system of electrons. This phenomenon, known as aromaticity, adds a whole new layer of intrigue to our understanding of organic chemistry. This is just the tip of the iceberg. Stay with us as we delve deeper into the fascinating world of benzene and aromatic chemistry. To get to grips with aromaticity, we first need to understand the Huckel rules. These rules, named after the German physicist Erich Huckel, are essentially a set of criteria that a molecule must meet to be considered aromatic. Firstly, the molecule must be cyclic. This means it forms a continuous ring of p orbitals, which allows for the delocalization of electrons. Secondly, the molecule must be planar. Because the p orbitals must overlap to allow for electron delocalization, the molecule must be flat. Thirdly, the molecule must be fully conjugated. This means that every atom in the ring must have an unhybridized p orbital. And lastly, the molecule must obey Huckel's rule of 4n+2 pi electrons, where n is any whole number. This rule ensures that the molecule has the right number of electrons for stability. So, let's take benzene as an example. It's cyclic, planar, fully conjugated, and has 6 pi electrons, which fits the 4n+2 rule, with n being 1. This makes benzene a prime example of an aromatic compound. These rules aren't just academic exercises. They're vital for understanding the chemical behavior of aromatic compounds. Aromatic compounds are exceptionally stable compared to their non-aromatic counterparts, which has profound implications for their reactivity. Now that we have a handle on the Huckel rules, let's explore how they apply to benzene. Ever wondered why benzene is so stable? The answer lies in a phenomenon known as resonance. Now let's talk resonance. Imagine a group of singers harmonizing. They are all singing different notes, but together they create a beautiful, stable sound. Resonance in chemistry is somewhat similar. In benzene, the 6 carbon atoms are not just connected by single or double bonds. Instead, they share their electrons in a way that creates a sort of harmonic stability. Benzene has a hexagonal ring structure, with alternating single and double bonds. But this is only one possible structure, or resonance form. The interesting thing is, benzene doesn't flip between these forms like a coin. Instead, it exists as a resonance hybrid, a sort of average of all the possible forms. This sharing of electrons over the entire molecule is what gives benzene its exceptional stability. It's like the molecule is constantly in harmony. And what about benzene's derivatives? Well, they play the same tune. Whether you add a hydroxyl group to get phenol, or a nitro group to get nitrobenzene, the basic resonance structure of the benzene ring remains. The added group might change the melody a bit, but the harmony of the shared electrons remains. Here's where it gets even more interesting. The added group can influence where new groups will add onto the benzene ring. This is called directing influence. Some groups, like the nitro group, are so-called deactivating. They make the benzene ring less reactive. Others, like the hydroxyl group, are activating. They increase the reactivity of the benzene ring. With an understanding of resonance, we can now move on to how benzene reacts with other substances. But remember, whether it's a simple benzene ring or a complex derivative, they're all playing the same basic tune of resonance. It's the melody of stability in the world of aromatic compounds. And it's this tune that makes benzene and its derivatives so fascinating to chemists around the world. Benzene doesn't just sit around all day being stable, it also reacts with other compounds in fascinating ways. Let's delve into one of the most common reactions involving benzene, the electrophilic aromatic substitution. This mechanism involves an electrophile, a particle that loves electrons, initiating the reaction by attacking the aromatic ring of benzene, which is electron-rich. Consider the halogenation of benzene, for instance. In this reaction, benzene reacts with a halogen in the presence of a catalyst to form a halobenzene. The catalyst, usually a Lewis acid like iron 3 chloride, activates the halogen to form a strong electrophile. This electrophile then attacks the aromatic ring, temporarily disrupting its aromaticity to form a sigma complex. But don't worry, benzene doesn't stay in this uncomfortable state for long. A base present in the reaction quickly removes a hydrogen from the sigma complex, restoring the aromaticity of benzene. And voila, we have our halobenzene. The same mechanism applies to other electrophilic aromatic substitutions like nitration, sulfonation, and the Friedel-Crafts reaction. The only difference is the electrophile involved and the catalyst required to generate it. Now, let's talk about the orientation and reactivity in monosubstituted benzene. When benzene already has one substituent, the position of the next substituent is not random. It's determined by the nature of the existing substituent. If the existing substituent is an electron-donating group, it directs the incoming electrophile to the ortho and para positions. If it's an electron-withdrawing group, it directs the incoming electrophile to the meta position. And what about reactivity? Well, electron-donating groups increase the reactivity of the benzene ring towards electrophilic aromatic substitution, while electron-withdrawing groups decrease it. So there you have it. The mechanism of electrophilic aromatic substitution in benzene. It's a beautiful dance between benzene and an electrophile, choreographed by the nature of the substituents and the conditions of the reaction. Electrophilic aromatic substitution is just one way benzene interacts with other compounds. Let's look at another, nucleophilic aromatic substitution. Benzene isn't just a one-trick pony, it also undergoes what's known as nucleophilic aromatic substitution. Let's dive into the fascinating world of this mechanism. It's a two-step process, which might involve either addition-elimination or elimination-addition, depending on the circumstances. In an addition-elimination reaction, the nucleophile, a species with a pair of electrons to donate, adds itself to the aromatic ring. This disrupts the aromaticity and forms a high-energy intermediate. This intermediate then eliminates a substituent to regain its aromaticity. It's like a guest arriving at a party and making room by persuading someone else to leave. On the other hand, in elimination addition, the process is reversed. We start with an elimination, where a substituent is removed, creating a highly reactive intermediate known as benzene. This benzene then quickly adds a nucleophile, like an open seat at a concert being quickly filled. Now you might be wondering, why would benzene, a molecule that loves its stability, willingly give it up? Well, it's a bit like stepping out of your comfort zone to achieve something greater. In this case, benzene sacrifices its aromaticity temporarily to form new bonds, and then works hard to regain its aromatic stability. Certain conditions favor these reactions. For instance, addition-elimination is more common with electron-withdrawing groups, which can stabilize the high-energy intermediate. Meanwhile, elimination addition is favored when it's tough to form the intermediate, such as when the substituent is a strong base. In both cases, the end result is a new aromatic compound, with the nucleophile taking the place of the substituent. It's a bit like a game of musical chairs, with benzene as the host and the substituents and nucleophiles as the players. With this, we've covered the major reactions involving benzene, but the world of aromatic chemistry is vast, and there's always more to learn. We've journeyed from the basic structure of benzene to its complex reactions, but this is just the tip of the iceberg. What a journey it's been! We've delved into the fascinating world of benzene and aromaticity, unraveling the intricate mysteries of chemistry. From understanding the Huckel rules that govern the aromatic nature of compounds, to exploring the phenomenon of resonance in benzene and its derivatives. We've seen how the unique structure of benzene allows for the distribution of electrons across its carbon atoms, a concept that's been beautifully illustrated with the resonance theory. This theory not only helps us understand the stability of benzene, but also provides a foundation for understanding the behavior of other aromatic compounds. We've also navigated the mechanisms of electrophilic aromatic substitution, dissecting each step of halogenation, nitration, sulfonation, and the Friedel-Crafts reaction. We've seen how the orientation and reactivity in monosubstituted benzene play a crucial role in these reactions, And let's not forget our exploration of the mechanism of nucleophilic aromatic substitution. We've seen the intriguing dance of addition-elimination and elimination-addition reactions, involving the elusive benzyne intermediates. But remember, this is just your starting point. There's a whole universe of aromatic chemistry waiting for you to explore. So keep questioning, keep experimenting, and keep discovering the wonders of chemistry. Stay curious, keep exploring, and don't forget to subscribe for more mind-blowing chemistry content.